In chapter 4.3, we take a look at an introduction to factoring. And before we get into factoring polynomials, for instance, I want to take a look at factoring in general. And factoring in general has to do with the fundamental theorem of arithmetic. Now, what this says is that any number greater than 1, for all numbers greater than 1, they are the product of prime numbers. So let's take a look at that. Here's 2, 3, 4, 5, 6. Let's go all the way up to 10. Let's go further. Let's go to 11 and then 12. And let's see how this plays out. Well, some of these numbers we know are prime. 2, for instance, 3, 5. Oop, I forgot 7. So let's go ahead and put 7 in there. 7 and 11. Those are all prime numbers. And what that means is that as factors, they only have the number 1 and themselves. 5, 1 times 7, and then 1 times 11. Now the other numbers on this list, 4, has more than just 1 times 4. 4 is also 2 times 2. So the factors of 4 are 1, 2, and 4. 6 is 1 times 6, but it's also 2 times 3. So let's rewrite that nice so you can see it nice and big. So 6 is 1 times 6, and it's 2 times 3. So 6 we can understand to be have the factors 1, 2, 3, and 6. 9 is 1 times 9, but it's also 3 times 3. So it has the factors 1, 3, and 9. 10 is 1 times 10, but it's also 2 times 5. So 10 has the factors 1, 2, 5, and 10. Notice all these numbers do have 1 in themselves, but they have other factors as well. 12 is 1 times 12, it's 2 times 6, and it's 3 times 4. So it has the factors 1, 2, 3, 4, 6, and 12. And in fact, we're still not getting all the way down to the fundamental theorem of arithmetic. We're just looking at what composite numbers have as factors. But if we take a look at 4 and just care about the prime factors of 4, 4 divides by 2. 2 is the smallest prime factor that goes into 2, and it goes in 2 times, and of course 2 is divisible by 2. So 4 is the product of the numbers 2 times 2, or 2 squared. Now here we're talking about the fundamental theorem. 6 is divisible also by 2. 2 is the smallest prime number that goes into 6. And when I divide 6 by 2, I'm left with 3. 3 divides by 3, and we're left with 1. So 6 we can write as 2 to the first power times 3 also to the first power. 8 is divisible by 2, and it leaves you with 4. 4 is divisible by 2. That leaves you with 2, and 2 is divisible by 2, and leaving you with 1. So 8, you can say, is 2 to the third power. And you might at this point be thinking, well, is it possible that all composite numbers are even numbers? 4, 6, and 8 certainly are even numbers, but then we come across the number 9. And 9, while not divisible by 2, is, however, divisible by 3, leaves you with 3. and 3 divides by 3 one time. So 9 is 3 to the second power. This is our fundamental theorem of arithmetic, where all numbers are the product of prime numbers. 2 times 5, those are both prime numbers, and that gives you 10. 12 is divisible by 2, that leaves you with 6. 6 is divisible by 2, that leaves you with 3. 3 divides by 3, and that leaves you with 1. So 12 is 2 squared times 3. That's the fundamental theorem of arithmetic, that all numbers greater than 1 are the product, are either prime themselves, like 2 and 3 are prime, or they're the product of prime numbers. Now, with that in mind, let's take a look at factoring polynomials. So let's apply that idea to factoring polynomials now. When we had numbers like, say, and I'll use a different number, 36, what we were doing is we were looking for a number that I can divide out of it. Now, 36 is divisible in a lot of different ways. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 5, 6 times 6. And so what we're looking for is, if we're prime factoring, we're going to try and find the smallest prime number that goes into 36. But we can also look for, if we're comparing 36 to a number like 48, we might want to look for the greatest common factor here. So let's see what 48 is. 1 and 48, 2 and 24, 3 and anything? Yes, 3 and 1, 16, 4 and 12, 6 and 8, and I think that's about it. And if we take a look at this list and say, well, what's the greatest common factor? What's the biggest number that I can divide evenly both into 48 and 26? And it looks like I have this number here, 12, and this number here, 12, as factors. And in fact, I'll give you different ways of finding common factors. But when we're factoring polynomials, it's a lot like this exercise here. What is the biggest number that I can divide out of both of these two numbers? Well, with a polynomial is one big number, but that number is made up of terms, right? There's a term, there's a term, and there's a term. And what I want to find out is, what is the highest, what is the greatest common factor between each of those terms? Well, out of each of these terms, 5, negative 15, and 5, I can divide out of 5. And when I look at the variable parts, I have x to the third, x squared. And if those were, well, and I have an x over here, so all of them have at least an x, but do they all have more than one x? Well, this one has three x's. This one has 2, but this one only has 1. Remember, when I don't have an exponent, I assume a 1. So it looks like, since 1 is the smallest, it's the most x's that they have in common, that's all I can take out. That's all I can divide out, is 5x to the first power. So if I divide that out, what am I left with? Right? For instance, if I divide 12 out of 36, I'm left with a 3. If I divide 12 out of 48, I'm left with a 4. So when I divide out 5x from each of these terms, if I were to divide out 5x, divide that, let's divide that one by 5x, let's divide this one by 5x. 5x cubed divided by 5x, those 5's cancel. X to the third over x to the first is just x squared. Alright, well, negative 15 divided by 5 is a negative 3. X squared divided by x is just x. And that and that both cancel to 1. They both divide into 1. So this is the factored form of this polynomial. So the polynomial now becomes a product of two factors. To drive that point home, let's try a couple more. Why don't we see what happens when we factor out negative 2x squared plus 6x minus 10. And what you're going to see is, for algebraic reasons, it's generally a pretty good idea to have the first term of your polynomial positive where possible. You don't have to, but it certainly helps. So for that reason, I'm looking at all three coefficients, well, my two coefficients and my constant term, which is also a coefficient. And I notice that they're all even. My first term has x squared, and my second term has x. My third term doesn't have an x, so I'm not going to be able to divide out an x. But since all of these are even, I can divide out a 2. But I want this first term to be positive. So in order to make it positive, 2 divided by 2 is 1, but a negative 2 divided by a positive 2 is a negative 1. And I don't want that. I want this to be a negative. I want to divide by a negative number so I can make this x squared positive. So I'm going to divide out a negative 2. That's kind of a long explanation, but you'll see how it works. So that's what they all have in common. So I'm going to divide this term by a negative 2. I'm going to divide that term by a negative 2. And I'm going to divide that term by a negative 2. And what happens is negative 2 divided by 2, well, that's an expression of 1. Any number over itself is 1, so I'm left with just the x squared. A positive 6 divided by a negative 2, a positive divided by a negative is a negative. 6 divided by 2 is 3, and I have that x still. And so a negative 10 now divided by a negative 2, a negative divided by a negative, again, is a positive. 10 divided by 2 is 5, and so I'm done factoring out my common factor. I got out my GCF here. My GCF was a negative 2. So now I ask myself, well, is this polynomial in here, is it prime? And in fact it is. There are some trinomials that I can continue to factor, and I'll teach you how to identify those in another video, but this one is prime. So I'm done factoring at this point. I cannot factor anymore. Let's try one more. This one we'll do by grouping so you can see how it works in the last couple of minutes here. This is by factoring by grouping. And this is an important skill set, so let's check it out. If I have y to the third power plus 3y squared minus plus 4y plus 12. I can group, if I say that I have 4 terms like this and I want to factor out, I can group my terms. Let's take these two, what's the greatest common factor of these two terms, and distinguish it from the greatest common factor of these two terms. And let's see how that works. Y cubed and 3y squared have only a y squared in common. Since there's no coefficient here, I can't divide out a number. And this one has y squared and this one has y to the third, so I can only take out the y squared. And when I do that, when I divide out y squared from there and from there, I'm left with y here. Those divide to 1, so it's y plus 3 there. Okay. Now a positive 4y and a positive 12 both have a positive 4 in common. And so when I divide that by 4 and I divide that by 4, I'm left with those cancel to 1, y. Positive 4 divided by 4 is a positive 3. Well, look at what I've got here. I've got y plus 3 here, and I've got y plus 3 there. So this term and this term both have in common a y plus 3. I can, in essence, factor that out. Now, what's happening here is I have two terms with a common term in common, and that common factor in common is y plus 3. So I can divide out y plus 3 from both terms. And when I do that, I'll divide y plus 3 here on the first term, and I will get y plus 3 over y plus 3 is 1. I'm left with y squared. And in the second term, I can divide out y plus 3 again, and again I have a factor of 1, and when I divide that out, I'm left with 4. And so here is the factored form y plus 3 times y squared plus 4.